radio research in India, pioneered by very two known figures, Professor Prof. and Shishir Mitra, who was the founder. Hello. Professor Shishir Mitra, you know that Shishir Mitra was the founder of our institute. Now, since I am talking on the National Science Day, I thought I'd show you this slide, and it shows that this is I just photographed from an article, old article. It shows that Raman is with his spectrograph. You know that actually another department also he described to some extent the work done by Sibina. Basically, he showed that wavelength of light changes with scattering by smaller particles, smaller than the wavelength of the optical waves. And these were changes occurs due to the interaction between matter and the light energy. And some light energy is transferred to the molecules of the scatter. That's why wavelength changes. And basically, Raman's experimental system was measuring the wavelength of light. Right? And of course, he mainly a spectrographic technique, spectroscopic instruments, and also he used some photographic plates and filter techniques to measure the wavelengths of the light. So this experiment was very clever type of experiment. Clever word is not very good, but it is a very ingenious experiment. Now, why I showed this, I emphasized on wavelength measurement because this legacy of wavelength measurements of light or electromagnetic waves was already there in Calcutta and Kolkata. And about 35 years ago, another scientist was measuring the wavelength of electromagnetic waves in a small laboratory, not very far from here in Westminster College. So we shall be dealing with that. We shall be talking mainly on that. So wavelength measurements already have a great legacy in Kolkata, starting from some basic course, seminar and of course others also. Now, when I start discussing the history of radio research in India, basically that was done in Kolkata. Then it was known as Calcutta, and the Calcutta was the place where this kind of experiments or this kind of science emerged. Whereas some places for that. And Calcutta was the oldest seat of learning of modern sciences in India, with the virtue of it being the capital of India, you know that. Until 1911, Calcutta was the capital. Right? You know that? Okay.
Huh.
And at that time, in the late 19th century, there are several institutes there in Calcutta. Royal Asiatic Society of Bengal, established in 1784. Then Indian Association for Cultivation of Science, of which you talk about in detail, and that was established in 1876. And that actually provided a platform for research to young scientists, young researchers at that time. But none of these institutes, nor Royal Aesthetic Society or Indian Association for Different Science, they provided any teaching curriculum, teaching facility. Only research facilities were provided. Then of course, University of Calcutta was established in 1857. Mainly we started as affiliating body, affiliating and examining body. We did not initially offer any courses. But it started science teaching in 1916 with the establishment of University College of Science and Technology, which is still going very strong. Mainly at the initiative of Sir Mukherjee. And of course, Presidency College was there. It was a very old establishment. It was established in 1817. But it had affiliation with the University of Calcutta in 1857 when Calcutta University was established. And it of course provided teaching in sciences. Presidency College was the only institute at the science which was provided before, of course, science. Sorry, 19 now. The Buddha. It is 1860. And now 19 years. 1960.
মানে এটা কিন্তু বোধহয় তখন বি কলেজ যেহেতু আমাদের আন্ডারে ছিল সেটা আমি
বি কলেজ কবে হয়েছিল?
বি কলেজ 1856
1856.
সায়েন্স কলেজ এস্টাবলিশ হয়েছে 1914
Science college teaching started in 1960. And what is
Physics
this?
department in 1960, the science college in chemistry started in 1914.
Gotcha. Okay. I got it from some. So, but B college, you were saying that it was
earlier,
okay.
almost as old as the university.
As well as the university.
In fact, from 1854 or 56, the same around that.
1854.
54 or 56.
Maybe I missed that. Okay. Then, pioneers of radio research in India, Sir J.C. Bose and Shishir Mitra. I'll be talking of them in more detail, but just I mentioned that Jagadish Chandra Bose began radio research in India during the period in late 19th century. And Shishir Mitra was a student of J.C. Bose and carried out very substantive research, radio research at the University of Calcutta. Maybe I'll put later. Now, if we look at the chronology of J.C. Bose radio research, J.C. Bose obtained his BA degree of Cambridge University and PhD degree of London University in 1884. And he was appointed officiating professor of physics at the Presidency College. And later, of course, he became a permanent professor. And very interestingly, on 30th November, it was documented on his 36th birthday, he declared that he would devote his pursuit of new knowledge. I don't know why he did that, but it was documented that on 36th birthday. And in 1895, in a public lecture in Town Hall, he demonstrated that electric waves can propagate through the intervening rooms over a distance of 75 feet, and the waves received were used to ring a bell and fire a pistol. Actually, he made a public demonstration of his system, and what he did, he put his radiator or transmitter in one room, and there was a relay, actually detector in another room, 25 feet away, and that receiver was that receiver triggered a relay, and that relay in turn fired a pistol and in a day. So that was public demonstration, and it was widely reported in local press. And of course, similar experiment was carried out in Presidency College as well. And J.C. Bose published his first scientific paper on polarization of electric rays by double refracting crystals in the journal Electricity. This was a very famous journal at that time. And of course, J.C. Bose research, radio research, has a very brief life. He only during 1895 and 1895 to 1901 he carried out research on microwave wireless system or radio research. But after that, he switched to another area of research, that is plant physiology and the effect of electricity, electric effect on plants. So he actually changed his research area from radio research to plant physiology. So there are some certain reasons for that, and he published 128 papers, and out of which only 27 papers were on microwaves or radio research. But
I just wanted to know for my own. So 1894, he declared that he will actually go for new knowledge, something like that, first for new knowledge. So 1895, then we demonstrated electric wave and copper. Then quickly switching to that. Then switching to wire.
no, actually he would start radio research, right? He's starting research because when he was in Presidency College, his main job was mainly teaching. But he was doing some research. He was inspired to take up radio research. There is a story I'll tell you. Radio research.
That story is hard to explain. That's 1867.
No, I'm going to come to that.
1867, Maxwell, when
I'm coming to that. This is not the end of the story, but this is the
story
start
of the story, the hard to read it, so I do it in my memory.
That's okay. Story is that the beginning of electromagnetic waves was Maxwell's equations in 1865, and Maxwell gave actually 20 equations. This was these are the original Maxwell's equations. But in the modern books, mainly 4 equations are in compact form, and this compact form was provided by 2 scientists. There was a step in between. Oliver Himself and Hamilton. Actually, they compacted all these 20 equations into 4 equations. So, I'm coming to it. Now, when Maxwell gave Maxwell's equations, what Maxwell postulated is that electromagnetic waves can be generated through the interactions between electric field and magnetic field. And he further stated that these electromagnetic waves will travel at the speed of light. And light waves and these electromagnetic waves are same. Only difference is in the wavelength. So that was also Maxwell's postulation. The problem was that this was the mathematical. Maxwell gave mathematical relations. How to generate electromagnetic waves? That was a big question at the time among the scientists. So ultimately, Henry Harsh in 1888 was able to generate. Actually, many other scientists also tried, but they could not show positively that what they generated was electromagnetic waves. Right? Now, Maxwell was the first person to clearly indicate that electromagnetic waves can be generated, and it can be propagates over a distance, and it also shows optical properties. That is the main case. Actually, a disturbance can, or any disturbance can travel, but whether that disturbance is traveling through waves or not, that can be only demonstrated if you can show that that propagation follows the optical principles. Now you can see that this was the original experiment by Hodge. Hodge generator was a smart gap generator, basically a smart gap generator. You know the smart gap? Small smart gap. High voltages are applied using a solenoid, and these sparks are generated. You know that now that sparks are broadband. It generates magnetic waves for large magnetic frequencies. So that waves were generated from this spark, and Hodge detector was also a smart gap. This is another smart gap, right? So what happened that whenever a spark was generated at this spark gap, simultaneously another spark was generated, and it was presumed by Maxwell. Or presumed means that it was shown by Maxwell that electromagnetic waves was generated at this point and it was now detected at this point. Of course, Hodge experiment was not confined to only this experiment. Hodge also showed that it followed other properties of optical waves. For example, it showed that interference pattern can be produced from this generation. And in fact, Hodge also measured the wavelength of these generated waves.
So suppose we replace that spark gap with Hornet. Suppose we replace those spark gaps to get by Hornet. Millimeter wave Hornet. Hornet.
No, Hornet was the receiver. I'm coming all those points. I'm just starting. Now, actually, when Jessico started his work on radio waves, then the scenario was like this. That we already mentioned that Hodge generated electromagnetic waves in 1888, and in 1891, Hodge used spark gap as a detector. Okay, but detector spark gap will not be the only detector. It has limitations. So Edward Branly in France, he devised another kind of detectors which was known as OAR. And that OAR is based on the radiation of conductivity of metallic powder under electromagnetic wave illumination. That is the metallic powder. Branly took a metallic powder in a container, and he measured the resistance across those metallic powder and found that whenever there is a radiation falls on the metallic powder or metallic filings, then suddenly the resistance drops. Okay, so that also can be used as a detector of electromagnetic waves. So that was Branly's invention. Then, of course, 1894, Lodge proposed a waveguide for generation, and Oliver Lodge also demonstrated at Oxford that most signaling can be done over a wireless over a distance of 60 years. And of course, very interesting and very impactful research was carried out by Guglielmo Marconi, and who actually started experimenting with radio waves in Bologna at his father's estate. and he used a small gap transmitter and and a coherent receiver for sending nodes to the distance over a distance of 2.4 kilometers. Now, of course, I come to your point. These were the things that happened. Then in 1894, Bose recognized the benefits of using millimeter wave. Actually, all these researchers are carrying out their experiments at longer wavelengths, say megahertz or kilohertz. Actually, Marconi was using kilohertz and Hart was using 66 centimeter waves. But those recognized that we could use small wavelengths, and if we can use the small wavelengths, then components required will be smaller. Right? The components required will be smaller one, and with those small components, the experiments could be more precise. That was Bose's idea. But there is also another anecdote. That is when Bose went to Business College to wanting some space, some laboratory space to conduct his experiment of Pusita. He was given a small room, not big room, not enough big room. So within that small room, he thought that he could only accommodate small sized equipment. So this is an anecdote. I am not sure whether this is true or not, but there is an anecdote. So that also inspired J.C. Bose to take up the millimeter wave. Millimeter is very significant in the sense that it stands apart from all those sizes. Very small wave. Millimeter wave, even today, millimeter generation is quite difficult. It is not as easy as generating longer wavelengths. Now, interestingly, when after Hart showed his system, that means electromagnetic wave can be generated, then two groups of researchers emerged. This is very interesting. One group researchers known as optically minded researchers, and another group of researchers were electrically minded. What do you mean by optically minded and electrically minded? Optically minded, their main objective was to explore optical-like properties of electromagnetic waves. Okay. Now, as I said that generation of electromagnetic waves and detecting at a distance was not sufficient to demonstrate that those electrical transmission of electrical disturbances were indeed electromagnetic waves. We have to show that it follows, obeys the properties of optical waves. For example, it suffers reflection, refractions, all those things. So they are known as quasi-optical properties. So this group of researchers had the main aim of showing that electromagnetic waves indeed follow the quasi-optical properties. And their key contributions were they developed a variety of detectors, polarizers, high frequency transmitters. Because as I showed you that to demonstrate the optical properties, it has to be within the laboratory, like reflection or refraction or polarization. These cannot be done in open air. At least in the technology at that time available. So they mainly worked with small wavelengths. For example, 66 centimeter by Hart, 5 millimeter by Bose. And actually these laid the foundation of quasi-optic, which later became microwaves. And key figures in this group were Hart, Lord, Reedy, Fleming, Raleigh, Lebedev, Bose. So all these scientists were mainly engaged in optical research, quasi-optical property demonstration research. But another group who were mainly interested in using the electromagnetic wave as a means of communication. For example, whether they can use the electromagnetic wave for wireless telegraph. And their main focus was long distance wireless telegraph. And for that purpose, they have to have high powered waves. High power can be generated only at low frequency because then you can have larger antennas and it is much easier to generate high power large antennas. So their systems are all mainly low frequency systems and their key contributions were large antenna, high power transmitter, tuning circuits, all those things. And Tesla, Oppo, Brown, and Harmonics. They were the main researchers who were engaged in this electrical minded experiences. Now, I was mainly focused on the body of this scenario. So there are, as I mentioned, there are scientists. For example, I already mentioned about Henry Hodge. I showed you the original equipment, but this is the schematic representation. This was the spark gap where the electric waves were generated. And this was another spark gap where it was detected. Actually, these metallic balls were put to increase the capacity to loading. That means larger amount of charges to be stored, which would discharge. And so that wave generation could be sustained for a longer time. So that was the idea. And as I mentioned that, Hodge used some kind of cylindrical reflector. See that these cylindrical antenna reflectors made of wax, and he demonstrated many optical properties. For example, actually, Hodge generated some interference pattern, and from that interference pattern, he measured the wavelength. You know, that maximum minimum distance between maximum and minimum. We could find out, and from that, he could generate we could measure the wavelength of this wave. Now there are other scientists also, actually his system was slightly different, and he had 3 small gaps instead of having 1 small gap. He had 3 small gaps, and his wavelengths were 7.5 centimeter and 20 centimeter. There are other scientists also. Then Oliver Lodge for the first time put his generator using a waveguide. You see that he for the first time used the waveguide. And he generated 7.5 centimeter and 20 centimeter. Then, of course, Lebeda was a Russian scientist, and Russian claimed that Lebeda was the pioneer of nuclear because he developed components which were very small, 100 times smaller than hard stone. So there are also scientists who tried to generate. But this is not well documented. Elevator work is not very well documented, as Jesse was saying. Then Fleming actually used prism. This prism and lenses. They are made of paraffin, and he showed the other properties of the optical wave. Was optical waves? Refraction, then refraction through lenses. So there are the scientists who worked on that. Then, of course, you come to in Calcutta. I already mentioned that he extensive work on quasi optics properties of electromagnetic waves, and he in fact generated 5 millimeters to 2.5 centimeter waves. So 5 millimeter. Do you know what is the frequency for 5 millimeter? To 60 gigahertz. 60 gigahertz is still very difficult to generate. And still 60 gigahertz has been used for certain kind of communication. You can imagine that in 1890s, Jesse generated millimeter wave. And this was the diagram of Jesse Bose's system, and he put his generator within this rectangular box. He used rectangular waveguide. This is his bench. This is the mirror. And this is the antenna. What Jesse Bush called as collecting funnel. But that was basically a horn antenna. Now it is well recognized that J.C. Bush was the inventor of horn antenna. Now a book, textbook. and just behind the horn antenna there was a spiral string detector, and that detected output was applied to a galvanometer, and the deflection in the galvanometer, J.C. Bush could recognize that wave has reached this horn antenna, and this is the horn antenna, and he used different kinds of other components like prism, double prism, crystal detector. So all these components he developed. Now, major contributions of J.C. Bush were this, he developed, I already mentioned, he developed transmission and reception system for 5 meters to 2.5 centimeter wavelength, and created a kind of spectrometer for ceramic meteorologies. And he also measured wavelengths of the instruments. He devised a system by which he could measure the wavelength of aluminum waves, and he determined refractive indices and electric constant, dielectric constant of materials and material waves. And as I showed you in the earlier slide, that he also innovated many devices, for example, microphone, artificial dielectric. These artificial dielectrics or so body paper. Wave guides, I already mentioned that we developed rectangular wave guides, horn antenna. Then there are some breakthroughs. Actually, J.C. Bush was the first who popular use crystal detectors. That horn detectors are talked about landing and others. But their detectors were really rare. But J.C. Bush was the first who used crystal for detection. I will come to this point again. And he also developed one contact detector. This is now recognized to be the precursor of the type. And he developed also double prism attenuator for microwave signal. This is very important innovation of J.C. Bush. I discussed this. And demonstrated millimeter waves like behavior, and they are using signaling. I already mentioned that he also did signaling. He showed the signaling capability of millimeter waves. That means he could trigger something by millimeter wave by generating the millimeter wave at a point, and then that wave travel a distance, and that could be utilized for some kind of signal. So these were the major contributions. Now, this is the generator J.C. Bush developed. Actually, our radiator I showed you, our original radiator was like just this one. But later, of course, Arch inserted one metal bone, which acted as a external resonator. And that actually gave the frequency sensitivity of the radiation. You know that broadband servers, they generate wavelengths over a wide range. So if one would have the wavelength at a certain wavelength, electromagnetic wave at certain wavelengths, then some resonator is required, and hard used a spherical ball. And following the hard system, J.C. Bush also had a system like that. But additionally, he added two metallic hemispheres. What happened that when spark occurs, this metal ball just vibrate at this certain frequency, which is commensurate with the size of the external resonator. So here also you see that J.C. Bush had the same system, but he used a two metal hemisphere. What happens there? When this metal ball vibrates, it actually touches these two modes and its surface gets roughened. So that roughening of the surface actually attenuate or it causes decay of the signal within a very short span of time. So what JC Bose did, they put two metal hemisphere and two platinum beads were attached to that. So when this metal vibrates and it hits the platinum beads, so platinum beads actually does not cause any roughening of the surface. So that was very clever idea, and that's why Bose could get a sustained oscillation over a longer period of time compared to Harsh. Okay. Now I already mentioned that this is the point contact detector. This is Bose and this is the system, and you can see that this is the point contact detector. This is actually initially he used galena crystal for this receiver detection, but he also galena is red sulfide. He also studied the other substances, and he measured the radiation resistance of the different detector. And this is the graph. Actually, you can see that along the x-axis, the atomic weights are given and for different kinds of material. And they found that in some cases resistance increased, in some cases resistance decreased. So he coined the term electric touch to classify the test materials as positive or negative. Positive means that resistance decreases with the radiation, negative means that resistance increases with the radiation. So these two categories of substances classified. And of course, also the resistivity of the receiver did not decrease or increase monotonically. So nonlinear arbitrary, you know that. So this is actually suitable for detection of the electromagnetic waves. So that was the perfect experiment Bose did. The David Moore was a subtle object in 1977. One that J.C. Bose was at least 60 years ahead of time. Actually, these kind of positive charge and negative charge. These are the some kind of precursor of P-type and N-type. Okay. And J.C. Bose empirically demonstrated the semiconductor phenomena through his coherent experiments, reading the theoretical understanding materials. Actually, semiconductor was invented in 1948. So you can see that before much before that, J.C. Bose did all these experiments, and his exploitation of material interfaces to actively control electrical conduction laid the groundwork for solid-state electronics, a paradigm shift in the 20th century. So, semiconductor physics was first, semiconductor properties were first demonstrated by J.C. about more than 55, 60 years ago. So that was remarkable. Of course, J.C. Bose could not explain why this P-type and N-type are occurred, but he explained and he put forward the result. So, J.C. Bose and the Olympic method actually, despite having many innovations, J.C. Bose did not prefer to patent his inventions. But except in the case of this galena detector, he got a US patent in 1904. This was the drawing in the patent document. You see that this is the there's a bias across the terminal to adjust the sensitivity. And it was claimed that this system can detect light beyond the violet or below the infrared in invisible regions of the electric radiation. So that was claimed in the patent document. And
Sir, according to Google, it states that Michael Faraday was the first person to observe semiconductor effect in 1833.
এটা আছে যদি হিস্ট্রি অফ মানে এখন অনেক কিছু বলা আছে ফ্যারাডে আমি দেখেছি শুধু মাইকেল ফ্যারাডে আমার অনেকের নামে দেওয়া আছে কিন্তু এইভাবে কি বলা আছে
না,
এইভাবে বলা আছে একটা ডিটেক্টর হিসেবে বলা আছে এটা ইলেকট্রোম্যাগনেটিক ওয়েভ ডিটেক্ট করছে
That was the greatest experiment.
মানে এখন অনেক বেরোচ্ছে অনেকে আমি I have seen also that history of semiconductor there are many evidences of semiconductor problems to that. So, but in the case of electromagnetic detection, I think this was the first to show that semiconductor can be used as detectors. And he actually provided experimental evidence. Maybe there are others. And Bose called it radiometer and compared it with the attention radiation. Actually, he called it attention radiation. He also viewed the picture like this and identity. Okay, very quickly, this is the double phase attenuator. This is another very important innovation by scientific discovery. Now, you know that if these two prisms, they touch each other, what will happen? The signal and mass signal without any attenuation, right? Now, if there is a gap, and the gap is sufficiently big, say in the case reciprocal gap is if it is greater than 0.1 lambda, then what will happen? Total internal reflection will not. No signal transmission, but all the signal will be reflected. Now, if the gap is below 0.11 lambda, then what will happen? That some amount of signal will be transmitted through and another portion will be reflected in this stage. And by adjusting this gap, you can in fact adjust the amount of radiation along this stage. That means this double prism system can behave as an attenuator. Right? So there are several applications now. You know that this kind of phenomena is known as frustrated total internal reflection, and this actually provided the evidence of photon tunneling, and Bose's work has been recognized as the first work on light performance. And this system can be used as waveguides and directional couplers, and this has been used in those 230 meter receiver. And Ikebasu, Professor Ikebasu has written a paper on this, describing details what are the implications of this double prism device by this. So this is I will go quickly. This is another system by which JC was to measure the wavelength. Actually, he used grating. These gratings are made of magnetic strips, right? And with the help of this grating and with the help of this bench, so we could measure. Actually, I'm not going into detail. So this is the receiver. This is the radiator. So by measuring this angle and following this kind of formula, basically measure the wavelength of transmission about 1.8 to 2.3 centimeters. And based based on this work, Mr. Ghosh was awarded Doctor of Science by London University in 1996. So this was the examination result. I put this photograph on this you can see that last week evolution progresses orange and experimental physics. So examiner was pointing and Thompson. So both actually devise many other components like wiring polarizer, twisted polarizer. So again, this is now recognized as the first intermediate. These are the modern version of twisted waveguide polarizer. These are the wiring polarizer modern. So that you can see as this polarizer was made by this. Now, thing is that I want to mention that this will switch to another area of research after 1901. And of course, quality of the research also dwindled down after that. So why? There are several reasons for that. First is that technological illuminations sparked discharge oscillator of microtheories. Magnetron invented in 1921. Then again, another major issue was that generating high power and micro frequency was not achievable at that time. So you require a high power system, micro generation for long distance communication. So long distance communication was not possible. And of course, poor understanding of the wave propagation also another factor. 1936, 89, although Lord Rayleigh gives some theory for waveguide propagation, but that was not sufficient. Most importantly, lack of demand. Actually, these researchers were not supported by industry, governments, or militaries until around World War II, 1937, and critical turning point, of course, World War II, and funding transformed the microwaves from theory to real world application. So when World War II, then there's a demand to develop radar, microwave radar, and so that that push from the military or defense actually was responsible for development of microwave systems later, after 50 years, 40 years.
Beautifully reasoned. Your reason beautifully.
What?
Your reason beautifully.
Oh, okay. Now, I mentioned that first long distance radio communication was demonstrated by Marconi. This is Marconi's very famous transatlantic experiments, and he actually transmitted signal from Kondu to England and received Newfoundland, Canada, and they are 2,000 miles apart. So such a long distance transmission was remarkable, and nobody could think of. And this was made done by Marconi. But Marconi unfortunately could not explain how such a long distance can be traversed by electromagnetic waves. You know that electromagnetic waves, if it is light wave, then it moves along a straight line and it will be obstructed by Earth's curvature. So one can actually calculate it that 167 kilometer miles is the maximum limit over which electromagnetic wave can be transmitted on the Earth's surface. But the thing is that Marconi was not discouraged by that theoretical calculation. He actually raised the cost of his transmitter. You can see that transmitter, and he was receiving the signal as he progressed, as he moved in a ship. He found that he could receive the signal at a very long distance. Ultimately, this was the experiment. But he could not explain how this happened. In 1902, Canadian Hillsides elicited the Marconi signal was propagated by reflection of signals on an RS layer in the upper atmosphere. So that was the postulate made by Canadian Insight in 1902. So Marconi and Ferdinand Brown, I'm not sure, we based often Ferdinand Brown. He also awarded Nobel Prize Marconi for his contribution towards wide aesthetic art. But I'm not giving that. In the Nobel speech, his academic chairman, he mentioned that although Marconi and Brown, they are ultimately able to have such a long distance communication, which is spectacular, but there are many contributors behind this. This achievement. Anyway, so this is the Canadian design layer. Actually, this was the drawing. This was conceptualized by the Canadian design. So this is the layer, and this postulated that this layer exists between 90 kilometers and 150 kilometers. Now, first, the discovery of ionosphere, of course, happened in 1924 when Edward Appleton and his student Miles Barnett, they carried out a series of experiments. Actually, they used British UBC transmitter. What they did, actually they just pointed transmitter towards upward, and the signal was reflected, and also the ground waves were also transmitted, right? So some interference pattern occurred, and by changing the frequency of the signal, they could find the distance. Actually, you know that 2D by lambda, by knowing the lambda, they could find the d. That means they could find the height. I'm not going to details, but they could find the height. And this height was possibly 16 miles, which matches with the Canadian heaviside's postulate. So that was the first evidence of existence of ionosphere. It was discovered by Appleton and Barnett. Now, at Kolkata, at Calcutta University, simultaneously, ionosphere research started. Shishi Mitra and his group. Very briefly, Shishi Mitra was a student, I already mentioned, and inspired by Bose's work. Mitra joined the Science College, University College of Science in 1916. And Shishi Mitra went to Paris. Actually, he did his JSc degree working with Sir C.V. Raman. And after going to Paris, he worked under Jardin and Marie Curie. But after doing work with them, he became interested in radio research, and specifically radio bar and its application. And he then went to Professor Gatton's laboratory of the University of Nancy. So that was a transformation from his own field to the field of radio research. Then of course Mitra returned to India, joined the University of Calcutta as part of professor, and set up wireless laboratory in the physics department. And for basic calculus. And wireless laboratory, the wireless research was significantly strengthened by installation of the country's first wireless transmitted calculus in 1923 by Indian states and experiments. And also Radio Club of Bengal formed around the same time, Radio Club of Bengal, so it's journal radio. Now, Shishi Mitra also established an amateur transmitter in the Boston Acoustic Disease, University of Calcutta. And the wireless laboratory at the University of Calcutta developed an indigenous equipment for ionosphere study. That is the major development. That means Shishi Mitra had some transmitter, and he actually following that circuits he started atmospheric research and conducted experiments on different layers of atmosphere. Published series of papers in the world-class journals, including Nature and Prof. So these are very prestigious journals. So if we look at the scenario of atmospheric research in 1930, so 1930, it was a pivotal period for atmospheric research in India. And this group participated in second polar year program. This is very important. Okay, so he joined the international community with his research, and he did many breakthrough experiments. 1933 annual solar eclipse, which confirmed that region's dependence on solar ultraviolet radiation. And he also showed the effect of cosmic rays and meteor showers on animation, particularly 1933 meteor showers. And of course, he expanded his research to ionospheric composition, high glow, active nitrogen chemistry, and geomagnetic and ionospheric interactions. All these areas. Oh, very quickly, I want to take 2 hours about Shishir Mitra to first active nitrogen. I'm not sure maybe first experience of alien experiments of alien was provided by Shishir Mitra. He published a paper on that. Now, interestingly, Mitra on that. Usually, at that time, considered receivers were a true paper, but he had his system where transmitter and receivers were located at the same location. So eliminating the need of two stations. And this is another interesting observation. I'm not sure whether you know that ionosphere has many layers. You know that? You studied ionosphere. Any students? Can you show the ionosphere?
সোমবার থেকে শুরু হবে স্যার
ঠিক আছে ionosphere has many layers, right? D, E, F. I talked about D layer. D layer was initially suggested by Canadian design in 1900. Then F layer was also there. And then D layer, which is below the E layer. D layer is around, let's say, 55 kilometers. Now, what happens? What is the difference between E, F, and D is that D is a not very well-defined layer. It is a diffuse kind of layer. So mainly its role is absorbing the electromagnetic rather than reflecting it. But that was obtained by Mitra's details. Also, actually what happens is that D can also reflect the signal partial, that is known as partial reflection. Partial reflection, from partial reflection you can find the ionization density of D layer. So that was the technique initially proposed by Mitra's group, and then that partial reflection technique was further developed by APD. So this is another very important findings of Shishir Mitra was that he got reflection. You know that D layer, E layer is there in the upper atmosphere. Why ionization forms in the upper atmosphere? Because at that point, atmosphere is very thick. So if ionization occurs, they're sustained, right? They're sustained, they last for time, for time. But it is not that ionizations are not formed in the lower atmosphere. Lower atmosphere also ionization formed. But they cannot be sustained. Why they cannot be sustained? Because density is very high, collision space is very high. If any electrons are generated or readily recombine, so ionization cannot be sustained for long. So if ionization is not there, then how reflection of electromagnetic wave will occur from lower heavens? That was precisely observed by Shishimito, and he got reflection from 20 to 30 kilometer range. Very interesting story is there. Actually, it is very good. That first, this was reported by in Science and Culture, and they wrote that initially it thought that this is seriously, but when it started getting consistent reflection, then to identify there must be some here. And in this nature paper, they mentioned that they named, Shishimitra named this layer as a sea layer, just to indicate that this layer is different from other layer, D, E, F, right? But Shishimitra could not explain readily what is the reason for this kind of reflection, from the neutral atmosphere. Much later, the reflection mechanism was attributed to the gradients in the radio refractivity of non-ionized layer. So that was later explained in that way. So I already mentioned that almost simultaneously, immediately after Shishimitra, Watson, Watt and others also confirmed radar echoes from the various layers in the troposphere. Right? And these early pioneering works are treated as a forerunner of HF radar. And atmospheric radar for probing the middle atmosphere developed in 1960s based on black sky radars. So you know that in Maitra we have a radar at 23 megahertz. You know that? ST radar has been known as ST radar, stratosphere troposphere radar. That was actually based on this principle. Right? So we had a connection of that radar with the initial observations of Shishimitra. Shishimitra book upper atmosphere is another milestone in the manuscript studies. And you know that part of this upper atmosphere?
Yes, sir.
I think that was so if you have a chance, you look at the book. You don't have to read. At least you look at the book. And this was first published by Asian Society in 1947. And in this book, Shishimitra presented a holistic approach to study the ionosphere as a part of complex system involving sun, earth, and atmosphere. And also he proposed use of radio waves to remotely sense the upper atmosphere and discuss the methods for immediately measuring the upper atmospheric temperatures and revealing the activity. So this is very interesting. Actually, Shishimitra in that book proposed how radio waves can be used to measure the different parameters of the atmosphere, for example, temperature. Right? So that is actually remote sensing, radio remote sensing. And also very interestingly, this book covered ozone formation, destruction, nitrogen oxygen molecule 90 growth, stratospheric imbalance, atmospheric cooling heating due to ozone. All these topics were covered. And you have to keep in mind that all this
Is that a really high temperature season? He used radio waves to remotely sense the upper atmosphere and discuss methods for directly measuring upper atmospheric
temperature,
revealing high temperature.
yes, very high temperatures.
Upper atmosphere.
And in some cases, actually, we found that
Upper atmosphere.
in some cases, I'm not sure which context I have related to this. In some cases, I have to check. Revealing high temperature means that maybe in some cases we found that what was conjecture that higher atmosphere will be low temperature. Revealing high temperature, okay, I have to check that. Anyway, measuring upper atmospheric temperature.
Sir, starting stratosphere warming এটা বলে হয়তো সেই হবে না।
Yes.
মানে ionosphere নাও
Stratospheric warming হতে পারে।
এসব ধাতু যেটা বলে
Actually, there is a phenomena known as stratospheric warming. So, in one of the chapters in upper atmosphere, Shishir Mitra discussed what could be the rocket experiments. Actually, he got those data from NASA's rocket experiments. And very interestingly, following those clues, our space program was formulated, a rocket program, which what experiments will be carried out in the space program. That was provided. And also, this was mentioned in somewhere that by Vladimir that when Russian launched Sputnik, they wanted to know some parameters of the atmosphere at the high levels. And they took the help of Shishir Mitra's book. It is written in a document. They took the help of Shishir Mitra's upper atmosphere to know the conditions of upper atmospheric parameters. Anyway, so you know that Shishir Mitra book and his research was widely acclaimed all over the world. And after his death, actually, John Radcliffe was a very renowned scientist. He wrote a memoir in the Royal Society. And he said that Mitra's reputation in international circuits is based on the writing of his book rather than on his original contribution. It is his book. And its writing required an author with an unusually sound knowledge of physics. No other one person has attempted to cover such a wide range. Fundamentals are treated so simply and so well that it still provides useful preliminary reading of anyone's starting research. Okay. So that was the words from. So there are many collaborators who became world renowned. You know that James Watt, he is the Rishikesh of Greek, he is A.P. Maitra, very renowned scientist, and he was a world renowned radio astronomer. All they are associated with Shishir Mitra research. So, in his later years, Shishir Mitra was concerned primarily with the teaching of radio science. And in 1944, he proposed a new department of radio economics at this university. And All India Council for Technical Education, they sanctioned grant to the university to establish the new department, Institute of Education and Economics in 1941. So that is the brief formation and history of our department. And this institute produced many eminent teachers, researchers in later years who took up the mantles of IITs, national institutions and other organizations in India and abroad. And Shishir Mitra was elected a fellow of the society in 1958. So this is a picture of a moon crater. You know that this moon crater was named after Shishir Mitra's crater. And the photograph of Mitra's crater was some photograph was taken of this by Chandrayaan 3 missions. So that is what I wanted to do.
lecture. So, any questions from the audience? We really had a long session today, 4 lectures today. So, if there are no questions, so I'll request Professor Shishanta Sen to solicit it as speaker to this model. Thank you, sir. So now we are moving towards the valedictory session. On behalf of the entire organizing team, I would like to thank our esteemed speakers, Professor Tony Maitra, Professor Shrikant Pal, Dr. Somnath Dotto, and Professor Animesh Maitra for accepting our invitation and enlightening us with their valuable and informative lectures. We are thankful to the Radio Physics and Electronics Association for being our associate and extending support to organizing this event. We would also like to thank our head of the department for allowing us to organize this event in our department. We also want to thank our teachers for their continuous support and encouragement. Thanks to all the staff members of this department for their cooperation. Thanks to all the volunteers for their hard work and active participation. And thanks to our participants for their graceful presence. So thank you so much. With this, we are at the end of today's session. Hope you enjoyed it. Thanks for coming. And now let us conclude the session with a nice